Hello friends, welcome to siddha.com. In our last video we have discussed about covalent bond formation, how a covalent bonds form it there. And as we know that covalent bond is directional in nature, and because of this property it gives shape to a molecule. So covalent molecules have a particular shape, right? A covalent molecule has a particular shape. But how to determine the shape of a molecule? There are three important theories that we're going to discuss. Number one is the valence shell electron pair repulsion theory, right? So this is the one theory that will actually help us to determine the shape of a molecule. And another concept is hybridization, right? Hybridization is a very important one and we will discuss it later on. But let me start with the valence shell electron pair repulsion theory. So basically these are the two theories that will help us to understand, to find the shape of a covalent molecule. Now let's start with the valence shell electron pair repulsion theory. This theory, in short we call it as the VSEPR theory, valence shell electron VSEPR, valence shell electron pair repulsion theory. To understand this concept, how to determine the shape of a molecule, first of all we have to find the total number of electron pairs around the central atom in a molecule, right? That is the main point of this VSEPR theory. According to this theory, it says that if you want to determine actually the shape of a molecule, right? Suppose we got here an ammonia molecule NH3, and we want to see what will be the shape of a molecule here, NH3. So what we will do, we'll just calculate the number of electron pairs around the central atom nitrogen there. If you see here, nitrogen it has a one lone pair of electron and it has three bond pairs also, right? So it has three hydrogen atoms and one lone pair. So first of all, according to the VSEPR theory, we will just calculate here the number of electron pairs, both lone pairs as well as the bond pairs around the central atom. And then the theory says that always a molecule will try to attain a shape in which it is most stable, right? It should be the most stable. Okay, that means a molecule will always try to attain the most stable shape. Most stable means it should have the minimum energy, correct? It should have the minimum energy because that is the most stable state. When we look at the number of electron pairs and the the number of bond pairs and the lone pairs around the central atom, according to the theory, these electron pairs actually they repel each other. Okay, you can say here this bond pair, the electron pair there, this one, okay, they will repel each other. Okay, so the number of lone pairs and the bond pairs around the central atom, they always repel each other, and because of that repulsion they will try to move apart from one another so that there is less repulsion. So as a result, the molecule has a minimum energy and the maximum stability. But the order of repulsion here is not same, it's different. If you have two lone pairs, the lone pair repulsion is maximum and the bond pair repulsion is minimum, correct? That means if you have an atom A, for example, and it has say for example there are lone pairs, right? Two lone pairs also there. This is a one lone pair and this one is another lone pair, and there are two bond pairs also, for example, right? There are two bond pairs also. The lone pair repulsion here, lone pair repulsion is the maximum. They have the maximum repulsion. Bond pair repulsion here is minimum, right? So you can say this is the bond pair and bond pair repulsion. Okay, so this is the maximum, this is the minimum, and then in the middle it is the lone pair and the bond pair, repulsion between a bond pair and the lone pair. Let me start with the simplest molecule, AB2 type molecule. That means I have an atom A and it is attached with the two B atoms, correct? And there is no lone pair around it. That means around the central atom A there are only two bond pairs, correct? This is the simplest molecule. And now, what are the possible shapes you can draw here? Suppose if I draw here a shape like this, if you have an atom A and atom B here, this is the one bond, and I can draw this shape. This is the possible shape. Here the angle between the two bond pairs here is 90 degree. Okay, this is a 90 degree bond angle here. Another shape that I can draw is, we can have an atom A like this, and you can have a bond angle a little bit more, around, let's say, 120 degree here in this molecule. And the third shape which is possible there is this one. You can have a linear one, so that the angle here is how much? It is 180 degree angle. Out of the three possible shapes, right, this one, the 180 degree angle here, is the most stable, right? This will be the most stable shape. Why it is most stable? Because here the groups are away, the bond pairs are away from each other, the angle is 180 degree here. The repulsion will be the minimum. So that's why this is the most stable, correct? Over here, if you look at this 90, the bond angle is lesser, the repulsion will be more. So that means if you move this bond pair here slightly away from it, if you increase the bond angle, repulsion will decrease, and it will be the minimum when the bond angle is 180 degree. That is why we find the molecules with AB2 type molecules, always their shape is linear and the bond angle is 180 degree. One of the common example is beryllium hydride, BeH2. If you look at the beryllium, it has 2 electrons in the valence shell. It forms the 2 bonds with the hydrogen atoms, and around the beryllium there is no lone pair, correct? You know, here the lone pairs are 0, but the bond pair, how many bond pairs are there? 1 and 2. There are 2 bond pairs. Okay, so the shape is linear. Any molecule, any AB2 type molecule with 0 lone pairs and 2 bond pairs, you can say the shape will be linear, because that is the most stable state. This is our 3D view of the beryllium hydride. In the center here is the beryllium, and the beryllium is attached with 2 hydrogen atoms. You can see all the atoms are in one line. So this is the in center, this is beryllium, and these 2 are hydrogen atoms. If I am rotating this molecule here, you can see all the time these 3 atoms, they will be in one line. So that's why the molecule is linear, and the angle here between the bond pairs is 180 degree, right? So an AB2 type molecule with 0 lone pairs and 2 bond pairs, the molecule is always linear. Atoms are in one line. Now let's take another example here. Let's take another molecule here. Let me start with the AB3 type molecule now. Now let's increase the bond pairs. We have, suppose again, lone pairs here in this molecule is 0, and suppose we have only 3 bond pairs. We have discussed just before that AB2 type molecule, you can expect that the molecule will have a linear shape, because that is the most stable state. Now if I introduce a one more bond pair here, correct? So let me start drawing a bond over here at 90 degree angle, right? So what do you see here? This is a 90 degree bond angle, right? Here also a 90 degree bond angle. This is the one, possible shape of the AB3 type molecule. But let me draw another possible shape. If I suppose here, if I draw another shape, and we will, after that we'll try to compare, right, the 2 shapes. The shape in which you find minimum repulsion, that will be the most stable one. Now let's take here, we have a bond pair like this, and now if I push this atom slightly over this side so that I can increase the angle from 90 to 120 degree angle. Now this is the atom B here, but the angle here is how much? It is 120 degree, and here also a 120 degree. That means we got a molecule in which central atom A is attached with the 3 B atoms, but the angle here is 120. Every angle here is 120, right? This is 120 degree and this one also has a 120 degree bond angle. So total is 360. That means all the atoms will be in one plane. So out of the two shapes here, we can easily say that the repulsion will be less with the B because the angle is more. When the groups are away from each other, repulsion between the two bond pairs will be less. So that's why AB3 type molecule always has a trigonal planar shape, right? This is what we call as a trigonal planar shape. Okay, that means this is just like a triangle here. In the middle of the triangle is the atom A, and these are the three B atoms joined to it, and all the four atoms, right? The three B atoms here and the central atom A. Okay, the three B atoms here and the central atom A, they will be in one plane. That's why this is a planar molecule, right? Trigonal, three corners here you can see, and planar, and the angle is 120 degree. One of the common example here is BH3 molecule. Boron trihydride. The boron there with three hydrogen atoms, one like this, another one like this, and another one like this. You can see around the boron, we know boron has only 3 electrons in the valence shell, so it forms the 3 bonds. So that means in this molecule there is no lone pair, only 3 bond pairs are there, correct? Only 3 bond pairs. So the molecule always attains a trigonal planar shape. So AB3 type molecule with 0 lone pairs and 3 bond pairs, the shape is trigonal planar. Have a look at this molecule. You can see the boron atom there in the middle, right? It is attached with the 3 hydrogen atoms, and the molecule is planar because you can see all the atoms are in one plane. I have the boron here, and there are 3 hydrogen atoms around it, and the angle here will be 120 degree. Every angle is 120 degree. Now what if you have an AB4 type molecule, right? Again, no lone pair. So I'll not talk about any molecule with the lone pairs. That is something we will do in our next lesson. Lone pairs, suppose here 0, and bond pairs are 4, right? Bond pairs are 4. So what will be the shape? There are quite a number of shapes possible. Let's start with the previous one. We learned that if you have an AB3 type molecule, right, the most stable shape is trigonal planar, in which the 3 B atoms and the central atom A, it is in one plane, and the bond angle is 120 degree. Now I have to introduce one more, because now here we have 4 bonds, correct? So let me draw here one more bond above this. So these 3 bonds here, these 3 B atoms actually are in plane, right? These 3 B atoms are in one plane, and now I am inserting one more bond pair above this plane. So that means if you have this plane and you are inserting one more bond pair, the angle here now will be what? It will be 90 degree angle, correct? This is one of the possible shapes, and here you can say the bond angle is 120 degree. But let me draw another shape, and let's compare then the two shapes. You see here that the angle here is 90 degree, and here the angle is 120 degree. If I make a little bit modification in this shape and try to attain a new shape, suppose if I push these 3 B atoms slightly down, right? If I push these 3 B atoms slightly down so that the angle here increases from 90 degree. So obviously I'll get a shape like this. We have an atom A, it is attached with the bond B, and now the 3 B atoms, which are actually in plane, if I push them down, so what do you get? You get slightly like this. You get a shape like this, isn't it? So you can say you got the 3 B atoms here like this. These 3 B atoms will still be in the plane, right? They'll still be the plane. Actually I have pushed them down, and once I push them down, the bond angle between these atoms here decreases. Okay, initially it was 120 degree here, but now it will decrease, and here it was a 90 degree bond angle. this was forming at 90 degree, but now it will increase. That means the angle now in this shape will be somewhere between 90 or 120 degree. It will be somewhere between 90 and 120 degree. It will be more than 90 but less than 120, because once I push the the B atom is here down, the bond angle will decrease from 120 degree, and at the same time the bond angle will increase from 90 degree. And now in this shape you will see that the bond angle here is 109.5 degrees, 109.5 degrees, and this is what we call as a tetrahedral shape, right? This is a tetrahedral shape, and out of the two shapes this is most stable, because here you got a 90 degree bond angle. So 90 degree bond angle means the repulsion will be more between the two bond pairs, and if you increase the bond angle from 90 to 109 degree, then it will be stable one, right? So out of the two, this second shape is the most stable one. That is why we say AB4 type molecule with 0 lone pairs and only 4 bond pairs, the shape is always tetrahedral and not like this. And the common example here is the methane, right? CH4 with the carbon, right, in the center and 4 hydrogen atoms around it, and there are no lone pairs, only 4 bond pairs. So the carbon will be right there in the middle, and the 4 hydrogen atoms will be like this around it. Okay. So this is what we call as a tetrahedral shape. Tetrahedral shape. And the angle here is 109.5 degrees. Here you see in the center is the carbon, and around it there are 4 hydrogen atoms, right? Tetrahedrally around it. And the angle here is, it's not 90, it's more than 90, but it's not 120. It is how much? 109.5. So every angle here is 109.5. Every angle, right? And that means this is not a planar molecule, right? Previously we have discussed that we have a linear molecule or a trigonal planar, but this is not a a linear molecule. You can see right in the center is the the carbon there, and there are 4 hydrogen atoms attached to it. Hope you got the concept. Thanks for watching the video. Bye for now.